Hello, everybody. Welcome to Friday Math Happy Hour. And this is my session for Math 1332. I'm going to go over the review for exam 3. And just before I start the review, I want to make a quick, I want to cover the topic of prime numbers as this is part of the review. And the first thing that I want to show you is I want to talk about what a divisor or a factor is. We often see this word of factorization, and they're basically divisors and factors are exactly the same. These are numbers that divide another number. So we say that A is a divisor of B if you can write down B as a multiplication. So this would be, so A times J equals B. There's a multiplication here. An example it is that 3 is a divisor of 6 because 3 times 2 is 6. So we say that both 3 and 2 are factors or divisors of 6. This means that both words are actually interchangeable. So whenever I say a factor, I'm talking about a divisor. So I'm going to use both words interchangeably. This leads us to prime numbers. Prime numbers are the building blocks of all of the numbers. And the way that you identify a prime number is that it has to be greater than 1. So this excludes number 1. 1 is actually called the unit. And it has to be greater than 1, and it has to have exactly 2 factors or divisors. The first prime numbers would be starting number 2. Remember that 1 is excluded automatically because a prime number has to be greater than 1. So this also excludes negative numbers. Negative 2 would not be prime because it's not greater than 1. The next prime number would be 3, and then 5, and then 7, 11, 13, 17. These are all numbers that are only divisible by 1 and by itself. That's why it has exactly 2 factors, 1 and itself. Each of these numbers cannot be divided, or it cannot be split into smaller numbers. When a number is not a prime, then we call it a composite number. A composite number is a number that is greater than 1, that is not a prime. So basically the ones that I skipped. Again, 1 is a skip. 1 does not classify as prime nor as composite. So the first composite number is actually 4. And it is 4 because the numbers that divide 4, it's 1, 2, and 4. Remember that a prime is supposed to have exactly 2 factors. So no more than 2, no more and no less. And 4 already has 3 because it has 1 and itself, the 4 itself, because 4 divided by 4 is 4. But it also has an extra divisor. So it has 3 factors or 3 divisors. And that's why it's composite rather than being prime. For the same reason, all of these numbers, 6, 8, 9, 10, 12, and so on, all of these are composites because they have another number that divides it other than 1 and itself. For example, 6 is divisible by 3. Let me put it on top by 3. 8 is divisible by 4. 9 is divisible by 3. 10 is divisible by 5. And I could just continue the list, huh? So all of these numbers are composite. Notice that in both examples, primes and composite numbers, I have the ... the ellipsis symbol at the end, which means that there's infinitely many primes and there's infinitely many composite numbers. One of our goals, as I mentioned, the prime numbers, because they are indivisible, these are the building blocks of any number. So if I give you a number, you should be able to write it down as a multiplication of prime numbers. So you could kind of like split it until you have all prime numbers. So in this example, we are asked to determine the prime factorization of the following numbers. This means that I want to write down each of these numbers as a multiplication of primes. My first number, 315. So I'm going to start by checking if it's divisible by any of the primes. Since the prime numbers are the building blocks, I'm going to use them as my starting point. So I'm going to write down the list of primes, which was, I'll put it somewhere in here, 2, 3, 5, 7, 11, 13. It is a good idea to write down these numbers and have the list of primes just in a place where you can quickly locate it and use it to solve each of these questions. So starting with 2, 315 is not divisible by 2 because it doesn't fit evenly. Often when you do this in the calculator, if you divide 315 by 2, you get a decimal. It would give you 157.5. So this means that it's not divisible by 2. Another way of doing this would be if you divide 315 by 2, let me do the division, it would fit 1, and then I'm just skipping the steps, but it does give me the 157 that I just mentioned, and the remainder is 1. So for a number to be divisible, the remainder has to be 0. Or if you're doing it in the calculator, because we're used to doing everything in the calculator on the computer all the time, then if you get a decimal, if you have the decimal point and numbers to the right of it, that implies that it doesn't divide it. So 315 is not divisible by 2. How about by 3? Well, it turns out that it is divisible by 3. And you actually get 105 because the remainder is 0. So the prime factorization, we do a diagram where we put 315. And because I divided by 3, I'm going to put a 3 here. And then I had a 105. My answer was 105, and I put it over here, 105. So the prime numbers, I'm going to list them on the left-hand side. And the composite numbers, the numbers that are not prime yet, I'm going to put them on the right. And I continue this process. Now divide 105. Remember that 3 isn't divisible because it's only divisible by 3 by itself and 1. But the one that I could split even more, that I could make smaller by dividing it, would be 105. So I go ahead and divide it by 3. So I started by checking that the original number, 315, is not divisible by 2. So I cross it out and move on to the 3. And it was divisible by 3, but I don't cross it out immediately. I need to check if 3 still divides. Like 3 could divide multiple times. So that's why I continue with the 3. I divide 105 by 3, and the answer is going to be 21. Well, actually, that's not 21. I think it's 31. Let me check the answer. Yeah, 35. So if you divide 105 by 3, you get 35. So let me put it here, 35. Okay, and I continue this way. 35 is still divisible by 3. And well, actually, that was a question. Is 35 still divisible by 3? Which the answer is no. So you cross it out and then you move on to the next prime, which is 5. And it turns out that 5 divides 35. So you put the 5 and then the answer, which is 7. And we know this because in this diagram, if you multiply the two numbers, it's supposed to give you the one that they connect. So 5 times 7 is 35. 3 times 35 is 105, and 3 times 105 is 315. So our goal is to have primes at the end of all of the branches. I'm just going to call them branches of this tree, tree. And the answer is going to be 315 equals, and since the 3 appears twice, I'm going to write it twice. 3 times 3 times 5 times 7. We could simplify this as 3 squared times 5 times 7. So when I have repeated primes, I write them in exponent form. Same thing, so that was the answer for A. I applied the same process for 273, which is B. So I'm gonna put my list of prime numbers again, 2, 3, 5, 7, 11, 13. Usually if you memorize the first ones, you don't really need like very big numbers, but it is possible to have very big numbers. Like I mentioned, the prime numbers are supposed to be infinite, so it just continues going on and on and on. 273, I would start by checking if it is divisible by 2. And one could tell quickly that it is not divisible by 2 because it ends on a 3. So all of the numbers that are divisible by 2, they need to be even. So 2 is not a factor, it's not a divisor. Next, I divide by 3. And it is divisible by 3. So 273, I divided by 3. I'm going to skip the steps, but I'm going to do it in my calculator. And that gives me 3. And the result of this division is 91. Continue. Is 91 still divisible by 3? Well, the answer is no. If you do it in your calculator, you're going to get one of those infinite decimals, like you'll get 30.33333. So it's not. Then I move on to the next prime. Is it divisible by 5? Well, you may know that a number, it's divisible by 5 if it ends on 0 or 5. Since 273 ends on 3, it's not divisible by 5. And I move on to 7. Is 91 divisible by 7? And it turns out that it is. And you get 7 and 13. And notice that 13 itself is a prime, so I stop there. So this is what tells us where do you stop. In the previous example, I stopped at 7 because 7 is already a prime, so I cannot split it anymore. And similarly, 13 is a prime number itself, so that's the end of this tree. I cannot go any further. And so then I look at all of like the end of the branches, which are 3, 7, and 13. And these are the ones that create the prime factorization. So 273 is equal to 3 times 7 and times 13. You could always check your answer by remultiplying. So on your calculator, if you multiply 3 times 7, that's 21. And then 21 times 13, that's going to give you 273. Okay, so now I'm ready. Well, actually, one more thing. So after we study the prime factorization, we also have a classification of numbers based on their proper factors. A proper factor is supposed to be a divisor or a factor that is less than the number itself. So now I'm taking away the number itself. For example, if you look at the number 10, 10 is divisible by 1, by 2, by 5, and by 10 itself. But the 10 is not considered proper because it's the same value. So a factor must be less, must be smaller than the actual. So the proper factors are only 1, 2, and 5. So 10 has 3 proper factors. Notice that because 1 divides any number, 1 is always going to be a proper factor for most numbers. Now, based on the proper factors, we're going to classify the numbers are perfect, as perfect, deficient, and abundant. It's going to be called perfect if the sum is, if it is equal to the sum of its factors, of its proper factors. It's going to be called deficient if the number is greater than the sum of its proper factors. and it's gonna be called abundant if the number is less than the sum of its proper factors. So let's do an example. I'm gonna look at the factors or divisors of the number. So if I have 6, the factors or divisors of 6, well, starting with 1, and then it is also divisible by 2, and also by 3, and then I'm just gonna do only the proper ones, huh? So let me kind of like, not just factors, because I don't want to include 6 itself. I gotta look at the proper ones. So I only have 1, 2, and 3. If I do the sum of this, 1 plus 2 plus 3, I actually get 6. So 6 is a perfect number because it is equal to the sum of its proper factors. Now let's do the same thing for 20. What are the proper factors of 20? It is a good idea to go in order, like but if you don't, just make sure that you don't miss any of the factors. This could be a problem when you don't do it in order, when you're not organized. You could miss one of those divisors. So I'm gonna start by 1, and then I'm gonna check if it's divisible by each of the numbers. Now I'm not using only primes. I'm listing all of the divisors of 20. Any number that divides 20 is considered a factor. So 1 divides it, 2 divides it, not 3, but 4 does, 5 does as well. 5, and then we also have, after 5, not 6, not 7, not 8, not 9. So 10, and usually once you get halfway, that's it, because the next number that would divide it is actually 20 itself, but that's not proper, so I stop there. So I'm going to stop my list halfway. And so these are the proper factors. Now I got to do the sum. So the sum is 1 plus 2 plus 4 plus 5 plus 10. And the sum is going to be, let me do this, 22. So it turns out that the sum is actually greater than the number. This is what we called deficient. Well, actually, the sum is, well, I'm probably should be written from the definition. This number is abundant because the number itself, the number that I started, is less than the sum, and that's actually what happened, huh? 20 is less than the sum because the sum was 22. So this is abundant. Okay, and last, I'm gonna do the same thing for 25, which is 25 would be 1 is divisible by 1, and then the next number that divides it is 5, and then it's also divisible by that's it. This one I don't need to go further away, actually, because these are the only two numbers that divide 25, 1 and 20. The next one would be, of course, 25, because half of this is actually 12.5, but I'm looking only for whole numbers, for integer numbers. So this is only divisible by 1 and by 5. We could probably check this because 5 times 5 is 25. So it only has like 2 factors. But you don't repeat the 5. You just write it once. And 25 itself is not a proper factor because it's the whole thing, the whole number. So the only proper factors are 1 and 5. If I add them, this is going to be 1 plus 5, which is, so the sum is 6. And of course, this time, the number 25 is greater than the sum. And this is when we call it efficient. The way that I would think about it to remember this is that you could look at the examples. A number that is deficient has a small amount, a very lesser amount, a few amount of divisors. 25 had only 2 proper divisors. And a number that is abundant in divisors. So it has more, because abundant, that's what it means, right? And perfect is exactly the sum is equal to the actual number. All right, so this should finish my introduction of prime numbers. For the review, I actually want to go over some of the questions that we did. Now, for these, I actually need all of my tables. So let me actually go ahead and pull out the tables. So I'm going to just very quickly get my tables. Remember that when we're making conversions, I need to have all of those symbols. And this may be something that you want to ask your instructor, like if you need to have all of those formulas before your exam, or if all of those formulas are going to be given to you. What I'm going to do is I'm going to just open the PowerPoints directly so that I can get all of the symbols that I need. So I'm going to be going back and forth between these ones. So to change a number from Egyptian numeral into Hindu Arabic, we need to remember the symbols. So this is our table with the symbols. Maybe I can just copy it and paste it in there so that we can have it ready. And so this is what an Egyptian numeral looks like, and all I gotta do is identify each symbol and count how many, and then multiply by its value. So it's kind of like 3 things, huh? Identify, count, and multiply. So notice that I have 6 of the pointing fingers, which is 10,000. So I have 6 in total. That's gonna make it 6,000 or 60,000. Let me write it as a multiplication. So 6, and each one is 10,000, so that makes 6,000. I also have 5 flowers. Each flower is 1,000, so it's going to be 5 times 1,000, which is 5,000. I also have 7 scrolls, so it's going to be 7 times 100, since each scroll is 100. So this is 700. I have 6 of the heel bone, so 6 times 10, because each one has a value of 10, so this is 60. And finally, I'm gonna count how many of the strokes, the vertical strokes, and this is actually 9. So it's gonna be 9 times 1. They actually have the value of 1, so it's just 9. Now I gotta add all of these numbers. And one of the nice things about the Egyptians is that because the Egyptians, they also have like base 10, because all of these are powers of 10. When you add them, you can just arrange the numbers in the position that they correspond. So this would be like 9, 6, 7, 5, and 6. So all of this numeral is equivalent to 65,769. Okay, so this is an example of how to convert Egyptian into, I often call these like the regular numbers, but every time I say Hindu Arabic, that's what it means, like regular numbers. So this Egyptian numeral is equivalent, or it represents 65,769. Okay, so the next example is, now I'm gonna do it backwards. I'm gonna write down this into Hindu Arabic. Let me see if I can copy my table. There it is. So now I am going to go, I'm gonna emphasize each, maybe what we can do is separate it as a sum. Like you could actually do like the expansion of the number, which would be, this is in the place of the ones, so that would be like 2 times 1. And then plus This is in the place of the tens, which is 0 times, well, 10 times. Well, let me write down the 0 first. Sorry. Um, see if I can erase it. There you go. 0 times 10. And then the 4 would be 4 times 100 because it's on the place of the hundreds. And then 3 is on the place of the thousands. So this is going to be 3 times 1,000. And 2 is on the place of the 10,000. So 2 times 10,000. And all of this is adding. So multiply and then add the next parentheses and add the next parentheses and so on. So now these numbers, the digits, they're telling me how many of each symbol. So I need actually 2 of the pointing fingers. So let me see if I can write it down. Kind of like this, huh? And then 3 of the thousands, those are the flowers. So I'm gonna have 3 flowers. And something nice about the Egyptian is that you don't really need to put them in order. So I could actually I could have it started on the right or the left. I'm just doing it in order, but it's not really needed. And then 4 of the hundreds, which is scrolls. So I could put the scrolls anywhere, as long as I have 4. I could put 1 over here. Then that's part of the number. Then the number it would be translated correctly. 0 of the tens, so I don't put no heel bones, and 2 of the ones, so I put 2 strokes, 2 vertical strokes. Okay, so these Egyptian hieroglyphs would represent the number in Egyptian. Huh? So this regular number, this in Hindu Arabic, 23,402, is equivalent to those symbols in Egyptian. Okay, so now I'm gonna do the Roman numerals. With the Roman numerals, you want to start probably, and not probably, that's the best way to start, from left to right, and then check that every time that you're moving, you actually have a number that it is smaller to the right. For example, if I start with M and I have a number to the right, which is smaller, so, and perhaps I need again the table of the symbols. I do know them, but I rather have them for quick reference for everybody, because otherwise I'm just gonna be saying all of this, and it's easier if we can just see them. So I'm gonna put it right there so that we can see it. So these are my Roman numerals. That's what they're equivalent. So the M is equivalent to 1,000, D is 500, C is 100, L represents 50, X 10, V 5, and I or L would be 1. More about 1/2 because we have the L over there. So I is 1. And I start on the left on the M, and I look to the right and I have a C, which means M is actually greater. So I want to go from greater to lowest. Greater to lowest. So because the next one is a lower value, the C, then I'm going to add the 1,000. Since I only have one M, then I add it. The next one, it's a C. But notice that to the right of the C, I have a D, which is a higher value because C is 100 and D is 500. This means that I'm gonna combine these two together in a subtraction. So they're gonna be like a single block, and I'm gonna subtract the larger minus the lowest. So it'll be like 500 minus 100, which is 400. And so these two together, I'm going to add them as a block. So it'll be 1,000 plus 400. Then I move on to the X, and I look at the one that is on the right, which is an L. Once again, instead of going to a lower value, it's a bigger value because X is 10 and L is 50. So this means I'm going to subtract them. So together, they're going to make one block, and it's going to be 50 minus 10, which is 40. So into my sums, I'm going to add 40. Then I move on to the next letter, which is V. And notice that the V is 5. And then to the right, I have a 1. So this is something that I can just add because I'm going to a lower value. You only subtract when you have a higher value on the right. So I add 5, and then I have a 1 plus 1. So these ones are at the same value. So these last three, the 5 and the i's, the V and the i's, I just could have done it as 7, huh? So 1,000 plus 400 plus 40 plus 7 would be 1,447. So this is my Roman numeral. MCDXLVII is equivalent to the number 1,547. Continuing this way. So now I have two M's, so that is 2,000 on the sum. And then starting on the D, the next value is a lower value, so plus 500. And then starting on the C, the next value is a smaller value, so that's going to be, because C is 100. And then and the I is actually a 1, huh? So that was correct. I had a larger value and then to the right a lower value. So it's a sum. But then when I get to the I, the one number to the right is actually a V, which is larger. So I'm going to subtract them. This is going to be 5 minus 1, which is 4. So I'm going to add a 4 at the end. So this number is equivalent to 2,604. 264. Okay, so next I'm gonna move on to, I think the next thing would be now doing it backwards. If I give you a Hindu Arabic number, can you write it as a Roman numeral? So right away I see the 1,000, so I can write down an M. And then I have 39. Remember that one of these symbols, the Roman numerals, let me copy them in here. Each letter can only be repeated 3 times as part of the rules. So as I write my number, I gotta keep that in mind, that I can only repeat each letter 3 times. So I started with the 1,000. And then the 39, well, 30, I can write it as 3 X's, and that would be within the limit, because I can only repeat it 3 times. And then to create the 9, what it would be wrong is, for example, to put a 5 and 4 I's, because I would be already repeating more than 3 times the I. So instead, the 9, you have to write it down as a subtraction, which is I and X, because that's going to represent, this is a single one, it's going to represent 10 minus 1, which is 9. So this is how I would write down that number. To do 959, I would do 900. Again, I could not use D and 4 C's. Instead, I'm going to take the 1,000 and subtract 100. So this is going to be CM. So that's 900. So it's like 1,000 minus 100. And then 50. To do 50, it's already there, huh? L. And then to do the 9, which is did it before, would be 1 and an X. And this is how we write down our numbers as a Roman numeral. Okay, so the next numeral system is the Babylonians. And remember that the Babylonians, they were base 60. And they have their numbers organized in groups, which you can actually see. Change that yellow color to a blue. You can actually see the 3 groups, right? So this would be on the place of the ones. This would be 60, and this is 60 square, which is 3,600. So if I'm given a number in Babylonian, to change it back, all I need to do is convert it, multiply it by its place value, and add all of these values. So first of all, each of these, let me see if I can erase each of these. So now that I've identified my groups, also to be remembered, and let me just take a look at show you where on my PowerPoints this is. So in section 6.2, you learn precisely this table is telling us that those are the place values. So from right to left, it's increasing in powers of 60. And then we also have that vertical symbol, that vertical wedge represents a 1, and the V or an arrow, sometimes my students call it the arrow, it's 10. So I'm going to go back and write down these numbers. So notice that I have a 10 plus 2, that this represents a 12 on the group of the ones. Next, I have a 10 and a 1, so this is 11 on the group of the 60s, because it's base 60. Always start on the ones or the units and then move on to the base. And the last group is actually 21, and then this is on the group of 6 square. And so now you could just do all of these operations. Let me write it down in different symbols, in different color. So do the multiplications first and then add them all to get the final answer. Let me make this smaller because it's huge. Okay, so this is gonna be 12 plus 11 times 60, which I'm gonna say is 660. And then 21 times 60 square. Don't forget to do the power first. You need to multiply. So when you do the power, this is 3600, which is also on the table. So if you have all of your tables ready, this is going to make it easier. Oh, wait, this is the other one. If you have all of these tables ready, it already has all of the power. So you can just directly use the 3600. So 21 times 3600 is equivalent to 65 and 600. And so the final answer, adding these three numbers, let me take a guess, is going to be 76 with 212. I'll check that answer right now. So let's do this on the calculator. 72. It seems like I missed a 60, 72. This 60, I forgot to include it. So the final answer is 76,272. Okay, so that's how to write down a number that is in Babylonian when you have the Babylonian symbols and you write it in Hindu Arabic. The other way around, what if you need to convert a regular number into Babylonian? Well, because this is base 60, the fastest way would be just repeat it. Any number that you want to convert into a given base, all you need to do is repeated divisions. So let's do our repeated divisions. If I divide 7821, which is 7,821, divided by 60, because that is the base, I actually get 130 on the top, and I'm going to skip all of the steps and I'm just going to put the remainder below. So often what I tell my students to figure that out, so you don't have to do the entire division, remultiply 60 times 30 times 130. So whatever number you have on the left with the number on the top, which is 7,800, and then subtract, and that gives you the final remainder. And it is the remainders that actually give us the answer. So the next thing is I continue dividing like that. So I'm gonna do 130 divided by 60 again. And this fits twice. It's 120 minus 1 is 10. And one more time, which is, well, actually, yeah, I always say don't stop, and I know other people does it the same way. So you're always dividing by 60, so the number on the left is 60. And stop when you get a 0, and this is where you're gonna get the 0 on the top. So you know that you stop, because 2 is no longer divisible by 60, because 60 does not fit into it. 60 is too big, huh? So it fits 0 times, and if you multiply 0 times 60, that is 0, and so the remainder is 2. So now, when you do this in the book, they actually organize it on a table where they have something like this. They put their numbers here, 7, 8, 21. They put the bases here, and they put the remainder on the other side. So like the division of this was, this gave me 130, and then they put the remainder 21 on the left. Maybe I should do it in a different color to avoid confusion. And then they do the process again, like, okay, now I'm gonna divide that 160 by 130, which is 2, and the remainder of that was 10, so they put the 10 here. And actually, they wouldn't continue going anymore because it doesn't fit no longer. So they would stop right there, and then they tell you, and I covered this, and this has been mentioned, that you're supposed to write down your numeral from bottom to top. So this number in Hindu Arabic would be, I'm gonna write down 2. Well, actually, the way that it appears, it's probably the best way. So so I will write down each one of them as from bottom to top. So I'm gonna start by writing, I'm gonna write it in this way. I'm gonna write the 2 first, and then the 10 and the 21 last, which in Hindu Arabic symbols, this would be, now this is actually on our section 6.3. Let me just show you again what I'm talking about. This is the diagrams that I am following. And so remember, I kind of like, so once you have your number, so from bottom to the top, we're gonna start listing the digits from left to right. And this is how you see it on this one. So this is pretty much equivalent. So from bottom to top, and then list them from left to right. So now the symbols, remember that because it's Babylonian, I have to use the vertical stroke and the arrows. So the 21 is going to have 2 arrows and a 1. The 10 is going to be actually 1 arrow, because 1 arrow is 10. And then this is going to be 2 strokes. And this is our answer. It has 3 groups, 2, 10, and 21. Okay, so that's how you convert a number, a Hindu Arabic numeral, into Babylonian. Another of the numeration systems that we studied was the Mayans. And since I have all of these already, let me just go ahead and show you the table. So on the Mayan numeration system, this is our base, which it has all of these powers. You also may have to remember or have what each symbol individually means. For example, a horizontal line means 5. So this is one group of numbers, the second group, the third one, and the fourth. This is equivalent, so it'll be 5 plus 5 and 2. This is 12. And then 1, 2, 3, 4. This is 4. This is actually the conch symbol. It's like a shell. It's equivalent to 0 and then 2. And when you're doing the Mayans, you actually need to start from the bottom. That's the place of the ones. So it's going to be 12 times 1, 4 times 20, because that's the next group value or the next place value, 0 times 360, and 2 times 7,200. And I don't have no more symbols. If I did, then I would use the next place value. Okay, so let's do all of our multiplications. This is 1280, 0, and then 7,200 multiplied by 2, that is 4,400. Finally, we add all of these numbers, and our final answer will be 4,492. So these symbols in Mayan represent the number 4,492 in regular numbers. Okay, so you probably know what I'm going to do next. Well, actually, no, you don't. This I kind of already did before, these examples, when I did base 60. But now we could also have any number base, like you can have base 2, which we call binary, base 3, base 4. The condition is that when you're in one of these bases, your only numerals or digits or symbols are less than the base. So if you're in base 4, you can only write down your number using digits from 0 all the way till 1 less, which would be 3. And in base 16, you actually need letters to have extra digits that represent 10, 11, 12, 13, 14, and 15. So all I need to do is expand these numbers to write it in base 10. Since they're in base 4, the expansion is going to have powers of 4. So I'm going to do, notice that this is the 1s, this is the 4 square, and 4 cube. So I'm going to have 1 times 4 cube plus 3 times 4 square plus 3 times 4. Let me write it down again. 3 times 4 plus 2 times 1. So this is, you could also think about it as 4 to the power 0, which is always a 1 because any number to the power 0 is 1. And this is going to give me 2 plus 3 times 4 is 12. Remember to do the power. 16 times 3 is 48, I want to say. And then 4 to the power 3, this is 64. Then you do all of the sum, 64 plus 48 plus 12 plus 2, and this is going to be 126. So 1332 in base 4 is equivalent to 126 in base 10. So similarly, as I mentioned, for this one, you need to remember you probably need to remember or have a table accessible with what each of the letters in base 16 means. We usually call it hexadecimal. So base 16 is called hexadecimal, and if you have the A, although here it might be confusing, I don't think they are shown before, unless I skipped it. Oh, it was here. I apologize. So after you pass base 10, then base 10 has digits 0 through 9. And then to represent the 10, you're going to need A, B is 11, C is 12, D is 13, E is 14, and F is 15. So when I go back, I remember I saw a B. So this is the place of the ones. This is the place of 16 because it's base 16. And the third one is 16 square. So it's going to be, the expansion is going to be B times 16 square plus 5 times 16 plus 1 times 1. Now I'm going to replace. B is actually 11. So it's going to be 16 squared times 11, which is actually 2816. And then 5 times 16, which is 80. And then 1. So my final, then I add all of these numbers, and my final sum is 2897. So this number in base 16 is equivalent to 2897. Okay, so now what if I want to do a conversion? I think this is the one that I thought we were going to do before because base 5 only has 5 symbols, but it doesn't include the 5. So it's from 0 all the way till 4. So I got to represent that using those digits. And this is where I do the continuous division, the repeated division. So I do, let me just write it down. Well, I do need all of them. I'm just going to write out all of them. It's going to be 1,844 divided by 5. And I'm going to do this in the calculator. And this is equivalent to 368 point something, but don't write down anything past the decimal point. Now I know that this is going to be 1,000. So now multiply and subtract, and your remainder is 4. And I continue. So I take the top number, 368, divided by 5. And this is going to be 73. And when I multiply, I'm going to get 365. And I subtract it, and I get 3 as a remainder. And I continue one more time, 73 divided by 73 divided by 5. This is 14, and I multiply, and it gives me 70, and the remainder is 3. And one last time, well, actually a couple more, 14 divided by 5, that's going to give me 2, and the remainder is 4. And this is really where I wanted to do the one where it doesn't fit anymore. So I use the 2 divided by 5, and it fits 0, so it gives me a 2. And in this case, I'm not going to put it like the book does it, but in this case, this would be the bottom. So from right to left, it goes in this direction. So I write down, so let me write it down, 1,844 in base 5 is equivalent. Starting from the right is going to be 24334, and then base 5. Which is the same thing that I did with the Babylonian, but it's just a smaller number, which is why I get more divisions. Okay, so to do sums in different bases, I have 5,625 plus 634, and they're both in base 7 and base 7. So I'm going to add them in like regular addition, and then I gotta convert it into the base. So 5 plus 4 is actually 9, but in base 7, 9 is actually a 1 and a 2. I'm just gonna put a small number, which means the base. So I'll put a 7 because it's a 7 plus a 2. And so I write the 1 and I carry. So you write down, you write down the 1 on the units, the 2, and carry the 1. So I put the 2 below and carry the 1. And just continue like that. So 1 plus 2 plus 3, that gives me 6. And in base 7, that's just 6. So I go to the next place value, 6 plus 6, that is 12. But in base 7, since I'm not allowed to use any digits bigger than 7, not even 7, so that's going to be 12. I can write it as a 7 and a 5. So 12 in base 7 is 7 plus 5. So I need 1 7, so it's 15. I write down the 5 and carry the 1 on top. And then I add 1 plus 5, which is 6. So my sum is, or my result is 6562 base 7. Okay, so I may have time for one last example, which is the subtraction. So this number is, I'm gonna set it up just how we subtract and add numbers. And they're both in base 6. And I subtract in the regular way again. 4 minus 1, this is actually 3. And then I kind of like encounter a problem because if I do 3 minus 4, 3 is actually larger. So I need to borrow 1 from here. So I subtract 1, so the 4 becomes a 3. But because we're in base 6, you're actually adding 6. So 6 plus 3 creates a 9. And if I subtract, because this is a subtraction, 9 minus 4, I get a 5. So by borrowing, I made this 3 into a larger number by adding the base. So if you're in base 6, you're adding 6. If you're in base 8, you're adding 8. And you're always going to get something bigger that you can now subtract. So 9 minus 4 is 5. 3 minus 2, this is, remember that since I borrow 1 is no longer a 4, so I use the 3. 3 minus 2 is 1. So the result of this operation, 434 base 6 minus 241 base 6, is equal to 153 base 6. Okay, so since I'm almost at the limit, I'm going to stop here and I'll see you next time. So I'm going to pass on the command to the host.
Thank you very much, Mr. Tintos, for that great presentation. So now I know the difference between base 6, 7, and base 10. So thank you very much for that great explanation. I would like to invite all of you to join us later on today at 1 p.m., where we're going to go ahead and have the TVE Student Success Victim Advocacy with Isela Grisels. Okay, and we don't have Happy Math Hour next week. Okay, so you can enjoy your Halloween without having to attend the Happy Math Hour. But we will be back on November the 7th, okay, where we're going to have geometry for Math 1332 and exam review 3 for 2412. The student success presentation will have a makerspace presentation with Daniel Martinez. Okay, so thank you very much for joining us. You'll have a great weekend and be safe.